Okay, welcome back. Yeah, the idea for today is just continue what we started last time. So what we were doing is we studying. Maybe I can be very brief. So previously, not really last time, sequences and when do they converge? That's very important. So we say xn converges to x if for every u neighborhood of x, you can always cook up some positive integer for which your sequence will live inside that neighborhood if you let your index grow big. And then we discussed how this really generalizes our idea from the reals or any other metric space. And we also introduced this idea of neighborhood basis at point. And then we discussed you don't really need to verify this condition for any neighborhood. It's enough to verify it at some just for neighborhoods in some basis. So last thing we kind of did was this definition. Want to repeat it now. This is from last time. So a topological space X is called Hausdorff if whenever you have two different points, X different from Y in X. So this is my capital X space. You can always cook up neighborhoods. Exist open sets U and B, which are disjoint. So the first set contains X, the second one contains Y, and they are disjoint. U intersects B trivially. So something I didn't really mention last time, but this is something that you should kind of expect from your topologies. If you have different points, you like your topology to distinguish these 2 points. That's what we're saying here. But there are also examples where that's not true. So yeah, it's a natural thing, but not always true. And we saw some examples, which I want to refresh now. Probably be more accurate with why things are true. So example 1, and probably this is what you should keep in mind. If you have a metric space, then it's Hausdorff. What I mean by this is the metric topology is Hausdorff. And why is that? If you take 2 different points, X and Y in X, if they happen to be different, then we have this distance between them. So here's your X, here's your Y. They will have some distance here, which is always positive. So if you go half that distance and you consider open balls, they will be disjoint. So then let's call this R. Distance from X to Y divided by 2 is a positive number. And these 2 neighborhoods, so of course this one is the neighborhood of X. It's important that R is positive, otherwise it's not a neighborhood of anything. And this neighborhood of Y intersect trivially. But that's something that requires a proof. How do we prove such thing? And I'm doing this because for the next homework assignment, you'll need to work with metric spaces. How do we prove these 2 things intersect trivially? We need to use the metric. We need to use some properties. That's very good. And another one, it's assume there is something in the intersection, and then compute the distance from x to y using the triangle inequality. And usually that's how I like to prove that two sets intersect trivially. Mostly if they are like similarly defined. So assume for a contradiction, we have something in the intersection. Well, I shouldn't call this x, of course. Let's call it z. So I'm assuming there is something in the intersection. And now we can compute the distance from x to y. Then the distance from x to y is smaller than or equal to the distance from x to c plus the distance from c to y. C lives here. That means this is at most r. And c lives here, which means this distance is at most r. 2r's is, by definition, the distance from x to y. So what we're saying here is the distance from x to y is smaller than the distance from x to y. And that's wrong. That's a contradiction. So what I'm trying to do here is when you go to do your homework with metric spaces, some statements seem very obvious. You need to prove them. Okay, so that's example number 1. Example number 2. Example number 2. If you, let me just say this, subspaces of Hausdorff, or maybe subspace of Hausdorff is Hausdorff. So part of this statement is actually realizing what I'm saying here. If you have a Hausdorff space and you take any subset within this topology, then it will be Hausdorff. And why is that? You take two different points. Let's go here. You take two different points in the subspace. You could have the neighborhoods on the big space. You intersect them with your subset, with your subspace. You'll get neighborhoods, which will still intersect trivially. So that's something that requires a proof, but makes sense. And let me start right here. I want to say, if we take a family of Hausdorff spaces, oh, maybe before I say this, yeah, maybe I can use this space to say something else. If we have T1 and T2 topologies from the same space, in which, say, T1 is coarser than T2, if X with the first topology is Hausdorff, that means you can distinguish points using these open sets. And of course, you can also distinguish them using these sets. So if X with the first topology is Hausdorff, so is X with the second. Right? If you can distinguish points using opens in T1, you can also use these opens to distinguish points using opens in T2. Okay, another example. 4. Now let's go to the collection. I have a collection here, xi, where I is in T, I is in lambda. It's a collection of Hausdorff spaces. so every space here is Hausdorff, then the product here is Hausdorff. And whenever you see a product which is not finite, you need to say which topology you are considering. But this one is going to be Hausdorff with both topologies. Both topologies, let's say T-prod and T-box. Okay, any idea why this is true? Well, first thing is, which one of these two topologies is finer? Or which one is coarser? Right, so we have T-prod inside T-box. Remember, for T-prod, we don't allow all boxes to be any subset. We just want the entire space. So only need to prove this for T-prod. Then it will also be true for T-box using part 3 here. So why is this true? If we have two different points, what can I do? Have two different points in the product. Remember, these are tuples or functions. If 2 points are different, they need to be different at some coordinate. That coordinate is Hausdorff. You said separate those 2 coordinates, then you can separate everything. So if that's the case, there is some coordinate for which x at that coordinate cannot be y at that coordinate. And now use xj's Hausdorff. And I want you to continue from here. You have x of j in some uj, yj in some vj, and they intersect trivially. So I want you to continue from here. Exercise, finish this proof. We need to cook up neighborhoods for x and y. And you only need this uj and vj. Is that okay? Okay. First theorem for today, which actually I mentioned last time, but I want to prove it now. So one of the important things about Hausdorff spaces, assume X is a Hausdorff space. Or maybe let's say if X is a Hausdorff space, then limits in X are unique. And what I mean by this is if you have a sequence, is such that xn goes to x and xn goes to some y, then x needs to be y. So this again is somehow telling you, well, this notion of being Hausdorff space is kind of a good notion. We are not saying if X is not Hausdorff, then you cannot claim this. I want to get there by the end of today. But we're saying if you're Hausdorff, then you're safe with limits. So proof. How do we prove such thing? Let's start with the sequence doing that. So let xn sequence in X with xn going to X and xn converging also to Y. So we want to prove X is Y. We want to show X is Y. How do we prove such thing? How do we prove these two things are the same? So let me say something that's absolutely wrong. X is the limit of xn, which is Y. Then X needs to be Y. Well, that's absolutely wrong. This thing is not well defined. Limit is not a point. It's a collection of possible values. So that's nonsense. So how do we show X is Y? Well, let's try to use X is Hausdorff. Of course, we need to use that. And Hausdorff, the powerful thing here is we need to assume, or we only can say things about different points. So assume that's not true. Assume for a contradiction, X is not Y. And here we need to cook up a contradiction somehow. Okay, if X is not Y, since X is Hausdorff, just a definition, there are open sets. U and V with X in U, Y in V, but the intersection is true. So we can distinguish X from Y using open sets. Okay, what now? Yep.
Grab the lowercase n or uppercase n such that when the sequence is past that, all of the points.
Absolutely. Here's our X. Here's U. Here's our Y. Here's V. Xn goes to X. So at some point, all values of the sequence will live here. Xn, xn plus 1, blah, blah, blah. They all want to live inside this U. First values, we don't really know. X1, X2 could live wherever they want. But then same thing for V. Points need to live here at some point. And that's just not possible. So since xn goes to X, there exists some, let's call this n1, such that, let me erase this, such that xn lives in U whenever n is at least at n1. Such that xn lives in U whenever n is bigger or equal than n1. And now same thing for Y and V. And here I'm using that U is a neighborhood of X and V is a neighborhood of Y. There exists n2 such that xn lives in V whenever n is bigger than or equal to n2. And now we're in kind of a problematic situation here. It's absolutely clear that this is wrong. It's not so obvious how to write that down, but it's absolutely clear this is wrong. How do we write this down now? We're saying if you surpass a certain value, then you're always here. And if you surpass some other value, you're always here. Yeah. Right. The problem here is we have just too many good things. We need to take one. So let's take n to be the max between n1 and n2. And then that xn is going to be problematic. and any other bigger than that one, but then x sub n lives in U, but also in V, which is supposed to be empty. And that's contradiction. And we're done. Yep.
Can I give an example where like the limit of a sequence are not unique?
Where limits are not unique? Yeah, we did that last time. For example, the worst example that you can come up with is take on any set. Well, you want more than 1 point, a set with more than 2 elements. Take the trivial topology. So every sequence will converge to every point because there are no neighborhoods.
Oh, I see.
But of course, that space is very far away from being Hausdorff. Yeah, and probably the point of today is I want to see how far away we are from the converse of this theorem. So that's a very good question. At some point, we'll get there, hopefully. Any other questions? So what I want to answer now is, at some point, I want to be able to see how far away we are from the converse of that statement. And that's where we're heading now. And that's the second part of the title for today's class. So here's our second definition. And kind of the problem here is sequences, they are, by definition, countable things. So we need to embrace that. We need to embrace countability somehow. Here we go. Topological space. Is said to be first countable if so. First here will come from something that's local. We'll see second countability in some weeks. If every x in X admits a countable neighborhood basis. So countable means you're countable as a set. Neighborhood basis is what we defined last time. Are we okay with this? So this will look like something we can enumerate using positive integers. So what this definition is saying, we have something like this, and whenever U is open, containing X, there's going to exist some n such that Pn is inside of U. That's what this is saying. Countable means this. Basis of neighborhoods means second. Is that okay? Okay, and now this is where things become. So today you're going to have one of my favorite kind of arguments or proofs, which are very like this argument. I think it's very neat. You really get to learn what's going on. You play with sequences. You're really using this notion of closeness. And today we're going to have some very interesting proofs. So example, unless, let's be honest, I don't want to lie to you. It's not that easy for me to give you examples that are not this one. I will give you some, which are sort of weird. But the example that you should keep in mind is metric spaces. And not only that, if you like these sort of pictures for your proofs, you should keep these metric spaces in mind. I'm not saying that the picture will be a good proof, but if you want to gather ideas from your pictures, metric spaces are very good. So if you take a point metric space and you take your favorite x in the metric space with a metric topology, what's going to be my collection of neighborhoods? Well, we know here, if we want the basis of neighborhoods at x, we can take an open balls center at x. Usually you need to consider any positive real. That's not going to be countable. If you restrict yourself to these balls, you're going to have a basis, which is countable, of course. One for each positive integer. Is the only thing I want to prove is that this is a neighborhood basis. It's absolutely countable, of course. I need to prove it's a neighborhood basis. How do we prove such thing? How do we prove that's a neighborhood basis? What we need to prove is something like this, right? Take any neighborhood of x, any open containing x, then you can always cook up one of these balls inside that set. So, in fact, if U is open and contains x, then we can cook up some ball by definition of the metric topology. Then there exists some positive epsilon such that that ball center at x radius epsilon is inside of U. So what they're doing here is something like, here's your U, here's your x. You can always cook up some open ball like this. To be honest, U should also be open. There's always some ball here, radius epsilon. By definition of the metric topology, the only thing you need to know to cook up now is some n such that 1 over n is smaller than epsilon, so that you're inside that ball. So this is, I don't really know how to say that there is such n, but we know there exists some integer such that 1 over n is smaller than epsilon. And then we're done. Then there's ball center x radius 1 over n is a subset of ball center x radius epsilon, which is a subset of U.
That I guess the Archimedean principle.
Right. So at this point, I should call this the Archimedean principle. But it's also just because at this point, we know sequence 1 over n converges to 0. So, which is just a consequence of that property. Okay. So we have our first example, and this is what you should keep in mind. Now, there is one thing about this example that's kind of better than just the definition of a countable neighborhood basis. Let's see if you can guess what I mean. This example, these countable bases have something a very nice property. What's that something very special? That somehow I feel you could guess. There's something special about that family of balls. It's not just a neighborhood basis, it's better than that. Let me, yeah, go for it. I could also do 1 over 2n. Just take evens. Will still work for some reason. Better than that. I mean, there's no way for you to be wrong. But what's going on here is this is the first ball. I can say the first one because they're countable, they are enumerated. This is the second one. This is the third one, fourth one, and so on. And that's by any means part of the definition. That's not part of the definition by any means. These neighborhoods, they are like nested. Can we prove that's always true? If you just have a countable basis, can you be sure you're going to have one that's kind of nested like this? We can. We can. If we have a first countable space, it's first countable. And we take any point in the topological space, then there is maybe, let's say, two things. Then one, there is a neighborhood basis, Vx, which is countable, so Vn's, such that they decrease. And now, the second part here is telling you, this is, don't call me on this, which is nonsense because this is being recorded. But the second point is going to tell you, you have enough sequences. In any first countable space, you have enough sequences. Enough convergence sequences. If xn is a sequence in X, is any sequence in X, such that in the set X, such that at the n coordinate, xn lives in your nth neighborhood, then what? Look at this picture. Each xn lives in the nested interval, in the nested neighborhood. Then needs to converge to X. Don't really care about what the sequence is. If it satisfies this, then it needs to converge to X. And there are plenty of these sequences in principle. Just pick for each Vn is a set, non-empty, of course, because it's a neighborhood of X. Just pick any value on that set. And now you do that for any n, you get a sequence. That sequence is going to converge to X. So this is telling you you have enough sequences somehow, enough convergent sequences, and you know how to construct them. Yep.
Say 1 and 2 or what?
No, both are the same. Following hold. The following hold. And what I mean by 2, let's be honest, 2 is not very precise. What I mean by 2 is if you take any basis with this property, then 2 will hold. Okay, let's prove this. So the thing that we know is that X is first countable. So let's fix some point in the set, in the topological space X, that's first countable. And the thing that we know is there is some countable neighborhood basis. So let Vx be some countable basis. I cannot use Vm because I want to use it for something else. So we use. countable neighborhood basis for X. Of course, here I'm using X is first countable. Or we should say, since X is first countable, these things exist. Okay, what can we do now? Here's U1, maybe X is here. Here's U2, U1, U2, U3, maybe, U4. Yeah.
Since they're countable,
Mm-hmm.
you could intersect all of them.
That'll be good. I could intersect all of them. That will be very good. Problem is, probably that will not be open. Right. If you intersect like the open interval -1/n, +1/n, then it will intersect at 0. That could be problematic, but you're very close. But almost. You're very close. Yeah. Uh-huh.
And then intersect them.
Right.
Because they exist.
So I'm going to do exactly. So I need to define this Bn. So for each n, I'm going to each positive integer. Instead of intersecting all of them, my Vn will just intersect from U1 to UN. That's your idea. But I need to do it partially. Then this thing is going to be a neighborhood of X. Why? Because it's an intersection of finitely many neighborhoods of X. And it's very important, it's finitely many. This is a neighborhood of X. So maybe you should verify that's true, because we never proved a finite intersection of neighborhoods is a neighborhood, but we know finite intersections of open is open. Each of these guys will contain an open containing X. Then the intersections of all these opens will be an open here containing X, and that's going to work. This is a neighborhood, and of course, and we clearly have Bn plus 1 is a subset of Bn, because I'm intersecting one extra subset. So the only thing that we need to prove is that this is still a neighborhood basis. So only remains to show that these things form bases. Now, very sadly, I'll need to continue somewhere else. Only remains to show that's still a basis. So how do we prove that's a basis? We need to take any neighborhood of X and show that some of these Bn's will be contained in that neighborhood. Now we know one of the UN's is going to be contained in that neighborhood, and then Bn is just a subset of UN. So let's write that. But this is basis just because we are taking smaller neighborhoods at each end. That's all that's going on. So remains to show, need to move the cameras. Only remains to show. I will continue here. Sorry about that. Remains to show this Bx. Yeah, probably need a new name. Let's call this Bx prime. No, I really don't want to do this. I should have called this Bx a different name because I'm claiming this is Bx. So this in the proof should be called Bx prime or something. So let Bx be the collection of the Bn's. So I want to show this is a basis of neighborhoods. Neighborhood basis of X. So how do we show such thing? We need to take U inside of X, open, containing X. And we want to show exists N such that Bn is inside of U. But since this Bx prime is a neighborhood basis, we know there exists some N such that Un is inside of U. And then Bn is Un intersection something else. So Bn is a subset of Un. It's Un intersection something else. Since Bn is a subset of Un, we also have, for that N, Bn inside of U. And that's all we need to prove. Well, that's part one. For part two, this is going to be an exercise. This will be actually homework assignment. But what's going on here is not suspicious. Take an interval. Sorry, take a neighborhood containing X. We want to show X and converges to X. Take a neighborhood containing X. Then some Bn is inside that neighborhood, what they're saying. That means all the other Bn's are also there, which mean all other Xn's also live there. And that's the definition of convergence. So what's going on here is given such U, which contains X, exists N with Bn inside of U. Then also, maybe let's call this capital N. Also, all other Bn's are inside of U. And we're done. So these arguments, I feel these are very neat. It's like very similar to what you do in analysis. But for some reason, at least for me, everything here feels like 1 over n converges to 0. I don't know. Any questions? Okay, theorem. So this theorem here is the converse of proposition 1 that I just erased, or it's probably here. Let's see. Yeah. The converse of this, here we're saying if X is Hausdorff, then limits are unique. So the converse will be if limits are unique, then X is Hausdorff. The converse called if you have enough sequences. So if X is first countable. Theorem 4. Assume X is Hausdorff. Sorry, first countable. And the statement is, I want to have everything in just one theorem. X is Hausdorff if and only if convergence sequence is in X have unique limit. So the proof, this direction here is always true independently of X being first countable. So this is just prop 1, don't need first countable. Now the converse, that's the new thing. This is what I want to study now. So do you see what I mean when I say there are enough sequences? If we only assume this, there are enough convergent sequences. If we only assume this, how are we going to prove this? We need to cook up open intervals, open neighborhoods. So here we're assuming our X is first countable. X first countable. And limits are unique. We want to prove X is Hausdorff. So we need to take X and Y, different points in X. And what we want, open sets, U and V, with X in the first one, Y in the second one, but they intersect trivially. That's what being Hausdorff means. So by our lemma, by the first part of lemma 3, there exist neighborhood bases. Let's call this Bx, which is just some Bn's. And let's call the second one By. Let's call these guys maybe Bn prime. Here, we know the things decrease. Bn plus 1 is inside of Bn, and same with primes. Just using my lemma 3, part 1. Because X is first count. So the picture is something like, here's our X. Here's our Y. We're assuming these 2 points are different. So maybe the first 2 neighborhoods intersect. Now let's be honest, maybe we can something worse like this. But the question is, can that happen forever? Well, the picture is clear, but the pictures are not enough. So here's X, here's Y. Doesn't seem to be possible we don't have any distance here that we could use as before. But at some point, it seems like this neighborhood should be disjoint. Okay, how do we prove that? And well, at some point, we need to use that sequences that converge will have a unique limit. So how do we write down our arguments? You can think about that while I raise this, which is not easy. So let me write the claim and see if claim there exists some positive integer such that these two neighborhoods of x and y intersect trivially. Why is that true? Let's assume it's not true. So let's assume for a contradiction that's not the case. Assume for a contradiction, Bn intersection Bn prime is non-empty for every n. Then for each n, there exists something in the intersection. Let's use Cn to denote that something that we're choosing. And now we can consider the sequence these things form. Now, have you heard about the axiom of choice? The axiom of choice is something like if you have a weird collection of sets, then you can choose one element in each set, and that will form a function. Like this here, we have sets which are not empty. We're choosing for each such set a point on that set, and then we're using all of them to cook up a function. Well, some years ago, there was some discussion whether that was always true or not, always possible or not. Seems completely obvious, should be the case. But the thing is, you cannot deduce this is always true just using the axioms from set theory. You need to assume that. This is called, since here we're like working over the positive integers, this is called the axiom of choice, but over a countable set. So countable axiom of choice. If you ask me, should be absolutely true. If it's not a consequence of the axioms, let's put it as an axiom. I hope you're okay with that. Because yeah, I don't have any. Yeah, unless you have a very good argument, I think you're okay. Now, if you're interested, you can Google why were people so not convinced about the axiom of choice. It's a nice idea. You will find some interesting claims. One of them is this makes sense, and then you can use it to prove very weird things. So yeah, Google consequences of the axiom of choice. I recommend you go down that rabbit hole. So consider this sequence. What about this sequence? The sequence lives in the intersection, right? So the sequence is going to x and also going to y. Lemma 3 part 2. Now use our lemma. Use, again, lemma 3 part 2. Since each value Cn lives in Bn, and these Bn's form a countable basis of neighborhoods which decrease, we know Cn converges to X. Just because at each n, Cn lives in Bn. And similarly, that Cn lives in Bn prime, we also know by the same lemma that Cn converges to Y. Now, what we're assuming here, this is the part where we use our assumption, convergent sequences have unique limit. So this is a sequence that converges to X and Y. Hence, these two things need to be the same. But that's contradiction. We started with X different from Y. Contradicts X different from Y. So the claim here is true, and we are done. Bn is a neighborhood of X. Bn prime is a neighborhood of Y. They intersect trivially. We're done. Any questions? So yeah, this is probably my favorite argument so far, because it's very instructive, and we're not using any crazy ideas. Okay, so now the question is, of course, we will not finish this today, but what else can we detect using sequences? You have a topology. What notions or what things can you detect about that topology using sequences that converge? And yeah, not a lot of time. Definition. We'll continue with this next time. Let's take two topological spaces. So the first thing I want to define is, what we're trying to do here is just focus on sequences. So the definition is, the first is a subset A of X is called sequentially closed. So this is what I'm defining. If for every sequence Xn, which lives in A, which converges to something, to some X in X, what we actually have is that X needs to live in A. So the picture here is something like, suppose you have an interval. We don't really know if we have the endpoints. So for this point, you have a sequence converging to that point. If the limit is also in the set, the interval needs to be closed. So that's what we're doing. If you have a sequence in the subset that converges to something, then the something needs to live in the subset. The other extreme, if you're open here, there is a sequence converging to that guy, but the guy is not in the set. So this is what we're doing here. Somehow getting to the boundary points using sequences. Of course, we'll investigate this more next time. And the second one is a function. So I want to use my second space Y. Function f from X to Y is sequentially continuous. And the good thing is this is local. So at some point X, if for every sequence sequence xn in X. If xn converges to X, then f of xn converges to f of X in Y. Yeah, and yeah, let me stop the recording here because we're on time.